All right, let's get started with our second talk. This is Sean McCarthy, Director of Product Video Platform, talking about bulletproofing large live events with the edge computer. He is from Paramount. I work with him on a weekly basis. He's drinking wine right now. He's in Boston. He stayed up late. He's on the East Coast. Give him a round of applause. Let's get going, Sean.
Cool. Hey guys, can you hear me? Okay, I do have a pretty bad echo now, so I don't know if you can mute things on your side just before we start. I didn't earlier. Okay, cool. It's better now. You guys can see my screen. Thumbs up. Okay, cool. Uh, so the title of my talk here, bulletproofing large live events. The with edge compute's a little misleading. I was going to kind of recycle some pre-canned materials and I decided to change things up a little bit, try to make it a little more interesting, a little bit more focused on some of the problems we're facing today. Though I'll mention those two edge compute applications. So yeah, looking forward to Sean McCarthy, Director of Product at Paramount Global. So our VTG group, a lot of you guys might know Dan, who leads the Portland Video Tech meetup there. We work on we work together on a central platform that powers a lot of the internal brands at Paramount Global. So think like Paramount Plus, Pluto TV, CBS Sports, News, etc. And obviously we do a lot of large events, and we see a lot of different challenges. And really here, I'm thinking Super Bowl scale events, maybe like NFL Sunday, playoff type games, not your typical, weekly live event. Really, some of these challenges that I'm mentioning here are seen during peak bandwidth utilization. So I'm really going to focus on the delivery portion of the workflow. That's where a lot of my day-to-day focus is. But yeah, here I kind of polled the team before the talk to validate sort of some of what I see as the biggest challenges. I added, a few others here. But essentially, dependency on third-party vendors. We obviously have to rely on third-party vendors. We use kind of best-in-class vendors for everything from transcoding. We're not going to build our own encoder, implement our own codec or anything along those lines. We're not going to build our own CDN. It just doesn't make sense. So having visibility into these sorts of systems at scale during these large events is a big challenge. Specifically on the delivery side of the house, we've noticed the past 2 years, the last mile internet congestion, the bottlenecks at the peering points, not even necessarily the CDN capacity, but the ISP capacity and just the peering agreements are egregious when it comes to streaming. We see very, very poor QoE on well built out networks, CDN flapping, and dive some of this. I won't read all the points here, but these are the types of issues that we see, and really what I'm going to talk about how we decide to address them, at least a portion of them. If we have time, we might talk about all of them, but I might get cut off before time. Product oriented talk and more of getting into some of the interesting nuances and details. So we'll see if time allows for that. But I do have to kind of preface the talk with these three services, right? Airspace is an API that really an interface into multiple. So a lot of the work that the caching working group within the SVTA is doing around standardized API interfaces, we've kind of created our own standardized unified interface for those sort of CRUD operations, purge, deletes, etc. Patches of CDN configs without each individual vendor supporting their own, or each individual vendor supporting a unified, API contract. So we've kind of normalized things, and it was a challenge, but it's essential to achieve some of what we're talking about here around automated purging, being able to patch CDN configs in real time, maybe remove origins, maybe remove a CDN altogether from a multi-CDN workflow, etc. Doppler, we'll dive into how it works, but it's essentially a traffic shaping system. Think, an in-house sort of homegrown NS1 Pulsar or Sidexis radar, along with the actual enforcing, the DNS element of it. And then Visors are real-time observability platform. So collecting raw logs, raw events, sometimes summarized metrics, but really raw telemetry wherever it makes sense from all of these different components, from signal acquisition through video playback. And that's really for getting to root cause analysis, the real-time observability, piracy monitoring. We'll talk about some of that. Session revocation really leans itself towards airspace, as does origin fail actions. But a point I want to drive home, and really part of what this presentation is about, is the fact that these sort of organically grew as one-off modular microservices, and there really is a need for now a unified platform. I bolded here unified interface, but really I'm talking about interoperability between these three products to make each one of them stronger in order to address these previous challenges that I had mentioned. So we'll dive into some of that. Just kind of our super high level overview. We have our transcoding and video processing service in this top box, which integrates with directly our configuration management API. Airspace creates the CDN configs for live events, sends all of the logs and the data into Visor, sending all the logs and data into Visor along with the video processing logs and metrics. And then there's also an integration with our Doppler system, so we know which CDNs to use, whether we're enforcing things at the DNS layer or rewriting manifests. And we'll talk about some of the pros and cons there during live events. But that's kind of at a super high level how these systems work together. And if we dive specifically into Visor, which is kind of foundational at the data layer to tying these different services together, we get something like this. So we're collecting raw logs from 5 different CDNs, some aggregate metrics from the video player QoE vendors. Observability with the correct metadata associated with them, so we can join this data set, is really what enables us to do some of the stuff that I'm going to talk about. So I just want to dive into some of the tenets of the data tracking, sort of the CDN side of the data collection, some problems we ran into and some just issues we have to think about. For us, we wanted the ability to perform distributor request tracing as well as session tracking. And it starts at the edge for us. So I know there's some, CTA initiatives around distributor request tracing, which starts at the client. There's a number of reasons why we're not really interested in right now, taking that sort of level of detail when it comes to the distributor request trace. And it's primarily because of CMCD, because we have a session ID now, which is really what we need from the client. To us, if the request never makes it to the edge, we're probably going to have some other client-side event or telemetry to use for debugging. And once the client actually establishes a connection with the edge and successfully sends a request, we can begin tracing individual requests and sessions from the edge upstream. So what I put here was just some VCL. We use Varnish and Fastly, so this is pretty universal VCL. We've kind of open source some of this, so anyone can really use this. But the idea here is to just tack on request IDs that each individual CDN vendor applies by default into the outgoing request header on forward requests to your shielding provider, or if you go directly to origin. And then we inject this VCL for Varnish and Fastly allows us to then inject that request header into the log line for the corresponding request. So we essentially append request IDs to build this sort of distributed request tracing system. And the session tracking for us is all facilitated by the CMCD session ID, which comes in as part of the initial edge request, in some cases request header, more often than not query string parameter. So we're able to really, and I didn't mention origin, we have for AWS anyways, and we have to extend this to Google, and it's all unfortunately going to be just different ways of implementing it. We have a way to return the AWS request ID to the on the response header to our shielding vendors, Varnish and Fastly, to get that origin request ID as well, and really just couple the full trace. One thing that I mentioned here is like mid-tier or intra-CDN logs. Some of the super pop CDNs don't really have this concept, but it was a challenge for us to make sense of these or decide whether or not we even wanted them. But in the case of sort of a tier-based cache hierarchy on your CDN, we've collected raw logs as if they were just edge logs, access logs for every GET request that was forwarded, and it really adds to the number of logs you have to request or that you have to process and ingest. And it also really screws up some of the timing data for each CDN. The timing data is different. In some cases it's the timing info, but on the TTLB or TTFB between the edge and the mid tier. In other cases it's the sum of all of them. So we've stopped collecting raw log lines from the mid tier, and instead have tried to replace them with what we'd call breadcrumbs. It's an Akamai specific terminology, but it's, I think, becoming kind of standardized in that there's essentially response headers that the CDN can communicate that has key pieces of information about the mid-tier request, maybe what the mid-tier IP was, some very particular timing info, and we can inject that into the logs as well. So we're able to kind of isolate edge from mid-tier, from shield, from origin. Another thing, and like this is kind of just setting the stage for really what we're going to talk about. The log normalization has been a huge challenge. There is an effort underway from surprisingly actually from the content security group within the SVTA to normalize some of this stuff. I think it makes a lot of sense that the content security group is interested in this, especially as we've repurposed some of these logs for piracy monitoring, which we'll talk about. But we had to do a lot of work to normalize the different, not just create metrics, but the actual raw fields that the CDNs expose in their log lines. So I won't kill the presentation to open the sheet and show you, but I'd recommend scanning the QR code. We kind of made this data dictionary, if you will, publicly available, and it shows how we've mapped different CDN log fields back to a common set of fields or a common really schema. And then in turn, the metrics that we've crunched and defined from those raw logs. And I just put an example here of how crunching a metric, in this case, it would be what I call a client abort. And that is a particular request pattern that really throws off a lot of other metrics. Specifically, it's when a client begins downloading a piece of content from the CDN edge, and then kills their connection, closes their browser, kills the app before the download is complete. Each CDN will log that differently, and in order to have a metric that captures that behavior on either a per request basis or something along those lines, we need to understand the logic for each CDN, right? And so that's just what I'm showing here: the difference of how Fastly would log it versus CloudFront, Edgio, and Akamai. And I chose this particular metric. We have a list of about 50 metrics we track, but this one, because a lot of the other metrics are dependent on this, right? In order to get, bandwidth, an accurate bandwidth calculation, or an accurate server time to last byte calculation, you need to filter out the noise. And in this case, this is noise, right? This is the CDN might be reporting bandwidth that it never actually delivered, or the timing info might be totally off. So for instance, looking in the CloudFront one, the TTLB can actually be greater than your timeout value. So you want to understand these nuances, understand how to generate these metrics, and then understand when to apply metrics to make other metrics more usable. So all of that work is kind of captured in this sheet. Happy to dive into it, happy to answer questions about it, but I'd suggest, if this interests you, taking a look at it. Another big thing is sampling data. This volume of data during large events it's almost unmanageable. It's on the order of gigabytes a second of log data, millions of rows a second of log data when we're talking Super Bowl levels, concurrency, or really anything around 1 million concurrents plus, 1 million viewers plus. You're talking about a massive log load if you're going to collect 100% of logs. Ideally, we have systems that are scalable and cost effective and performant, that we don't really have to worry too much about that, but we always have to balance the operational overhead and cost with the value that this sort of data collection provides the business, right? So sampling is a reality, and there's a lot of lessons learned with sampling. We have a lot of feature requests out to different CDN vendors for this, but essentially conditional sampling is very important. We want to collect 100% of errors, right? Or 100% of requests that maybe hit obscure pops or came from obscure geos, but we don't necessarily need 100% of 200 requests or 100% of Comcast requests, right? A very saturated network, if all of those look the same. So what we're really hoping for is the ability to conditionally sample based on session IDs. So we could say, hey, once a session begins, collect 100% of a given session's logs. That's a very challenging data science exercise. It's really statistical exercise for some of the CDNs, but that's where we're hoping we can go with this. But in the meantime, assuming it doesn't get delivered, we're toying with the idea of building out a sort of middleware, some sort of traffic-like system, or Red Panda. Like, there's a lot of different solutions, but basically a place for us to send all of our logs and then decide what we actually want to ingest and index into our database. We could put some of those sample rules there, and then that way just always collect 100% of logs. But of course, that adds overhead on our end, development effort, etc. By default, what we found was for large events at scale, collecting around 25% of logs is pretty good. It gives us a solid representative sample of various ASNs, various POPs, various end user behaviors, various device requests. But once you get below 25%, it's very shaky. We used to try to do 5% by default, just to keep costs down and keep things manageable. But there was just way too much noise. We tend to do 25 to 50%. When we can, we'll do 100%. But of course, with sampling, when it comes to the actual metrics, think client boards, bandwidth, server-side concurrence, cache hit ratio, all these different things, you need to compensate for the sampling when you're actually generating your aggregate metrics, right? So, you think for some it would be as simple as, if you're sampling at 50%, multiply a metric by 2. That's kind of what I'm showing here. Yeah, for some it works. For percentage-based metrics, it works. Error percentage, success percentage, or success rate, error rate, these sorts of things. For concurrence, and here we actually can derive a server-side concurrence number by hashing out the client IP, user agent, refer, using unique session IDs when they exist. We can compensate for those, but then there are some, especially the timing info and the count metrics, so not the percentage or rate-based metrics, but the error count, where you really can't add a multiplier. And if you're not sampling your errors because you want to see them, they're obviously going to be exacerbated in some regard. So you have to consider all of your sampling logic when making these multipliers to compensate for them. We have some best practices in that sheet that I mentioned before that if we have time I can get into, but I don't think we will today. But it's just something to definitely think about. So that's kind of an overview of the types of CDN data we're collecting and some of the challenges that, collecting and really deriving operational metrics that we monitor in real time, with eyes on glass, our operations teams are focused on during live events. But, that's really for root cause analysis. That's for troubleshooting and debugging odd issues. When it comes to automated means of actually routing around internet congestion or routing around availability issues, or even just transient, load or network blips, right? CDN load issues or network congestion. We don't rely on that data. We don't rely on anything manual. We rely on an automated CDN traffic shaping system, or really CDN decisioning engine. And this is something we built, homegrown. We have a lot of reasons why I would argue that media companies should build this and not buy this. You'll learn a lot about the data. It's pretty cost effective to do this now. And yeah, we dive into some of the reasons why, but essentially our traffic shaping system consists of 4 components. A RUM client, of which we've open sourced, and there's an SVTA project kind of kicked off to standardize the way a RUM client in a browser works, and B, what the performance metrics are when it comes to measuring CDN performance. So I'll dive into that. But this whole system consists of the client that generates the data aggregation and ingestion, the business logic, or creating meaningful, what we call route maps, or really stack rankings of CDNs based on some business logic. Could be cost, but for us it's performance. For this presentation it's performance. And then enforcing the decisions, right? So sending this data to third-party systems, be them DNS servers, manifest generation servers. Content steering is where we're going with this. Lots of promising work there to address some of the issues I laid out in that first slide. So this is essentially what we've built out, and a little how it works. So our browser, we have some JavaScript running on the Paramount web properties. So think, CBS.com, MTV.com, Paramount Plus, Pluto TV, etc. At some defined interval, as user it's a user input. So whoever decides to deploy this JavaScript can choose the interval after startup. So I think our default is 30 seconds. 30 seconds after a web page loads, this JavaScript executes, in which it will compile a task runner. And that task runner essentially just exposes a bunch of CDN endpoints, of which we're hosting 1.5 meg objects that are representative of video segments. They're TS files, but there's no actual video data in them. And we'll talk about the pros and cons of that approach. But it'll basically spawn a bunch of requests for these test objects. And in turn, at least the way it used to work, and there were some problems with this approach, we would generate performance and availability beacons on the client, use a CDN, specifically in this case it was Fastly, as a beacon termination endpoint, and ingest that data into in real time into a database where we can then perform our business logic and really stack rank the CDNs based on performance. We decided to perform all of our traffic shaping at a geo ASN level, so state ASN, wherever state is supported. So for a given user in New York on Comcast, Fastly performs best, Akamai performs second best, Edgeo third, et cetera, et cetera. In turn, we will steer cohorts of users at that aggregation at the geo ASN level to the most performant CDN. And that's a constant flow of beacons that are traversing the system and informing the traffic shaping. But some of the problems with this really lay in the fact that there was way too much noise in the client. The beacons that we were generating, we'd have to, basically it was multiple things, but each beacon required its own test object to be downloaded. So it was a lot of wasted bandwidth on the get side. And then in turn, each beacon was posted separately. So there was a lot of chattiness and a lot of, open connections and objects, even though they were small, being posted out. Over some of this, I won't. We're leveraging edge compute to reduce the complexity and of what the client is responsible for, as well as give us a lot more flexibility as to what we can do on the beacon generation side of the house and really on the data we can collect from the client. So all of this data is based on the browser's resource timing API. And we were basically calling that API in real time in the Doppler client previously, but now we call it, but we take an entire sort of data dump. We zip up the entire content of what the resource timing API is exposing, and we post one small gzipped file to an edge compute service. And we actually have, 2 edges that we're sending this to in case one vendor ever goes down, where then we're uncompressing it, hydrating it, doing some geo lookups, doing some lightweight ETL jobs essentially. And then we're computing those metrics at the edge. And that gives us a much easier, it gives us a much lighter weight approach to the client. There's a lot less noise, but it also gives us a lot of flexibility around making changes. We don't have to worry about pushing a JavaScript change or our tasks, changing our tasks list or anything like that um, in the actual Doppler client, and worry about breaking sites, which has happened in the past. Instead, we move all of that risk server side, where if something were to go wrong, the worst that's going to happen is a couple of red lines in the browser on failed post requests, and it would be completely transparent to a user, most likely. And we can iterate quickly. We could do a lot more tests, and we have observability. We couldn't really get raw observability into what the Doppler client was doing across all clients and all browsers. Now we're monitoring, one edge compute service. So there's one of your sort of edge compute use cases, but it was really around optimization of this client. So we ended up, here I'm just showing the consolidation of, 4 test object downloads, 1 for each beacon, and 4 beacon posts being consolidated into 1 test object download and 1 post. And here you can kind of see the work or the results of that work, right? This is just test object delivery. From a CDN perspective, we cut our bandwidth utilization by 75% just about. And that means 75% more bandwidth that a client has to stream video and just put towards what they want to do, not just tasks that the browser is doing in the background. The impact on video of actually using Doppler in production versus not. So like prior to, in this case, June 18th here, we were just kind of round robining CDNs, and you could see that the peak buffering was over 2%, over 1.5%. And then after our, several iterations of changes, we had a 33% reduction in peak rebuffering. Those are big numbers. When you're talking reducing buffering from 10% to 5%, there's a lot of ways you could do it. When you're talking about 1.5% to 0.5%, there's a lot. You have to take these really nuanced approaches, and it's still is a huge number of clients that received or are now experiencing better QoE. An example, availability issues. I didn't call out the vendor here, but there's a CDN vendor that no longer exists that experienced an outage. And the interesting part about this is it was an outage on select POPs due to a DDoS attack. So this is not something that like the CDN exposed as an outage, or that, if you were monitoring for a global outage, you would have captured and then removed that vendor from your mix. This was select POP. So only if you had users mapped to that POP would you see it. And in this case, we were measuring via Doppler, and we had some workflows on it and some not. And for the workflows that were not on it, the trend is on the left. That's the actual buffer trend. So there was about 40-minute impact of large rebuffering spikes. What you see on the right are Doppler performance metrics capturing the availability dips and the TTLB and TTFB spikes at the top. And really, with our ability to do the midstream switching based on that data, the clients that were on that workflow actually saw only a 2 to 3 minute outage with the time to switch between CDNs around 30 seconds. So when we're talking about large live events, these systems that are self-healing, that are self-aware, this is what we're trying to build to route around issues really before they become big spikes that like what you see on the left. And that becomes increasingly important with all the internet congestion we've seen and the trends that we've seen in the past year. So here I just linked a description of the project. I'd suggest reaching out. There's basically 2 things. There's a description of the goals, what we aim to achieve, how the client is going to work. There's already a GitHub repo it was called Open Insights. We're actually going to port everything over to an SVTA repo that is really focused on the tasks runner and the JavaScript that runs in the client. Then on top of that, we have best practices for defining the metrics, right? The TTFB, TTLB metrics, using those resource timing API uh, the resource timing API data. So that's all linked in this sheet. And yeah, we could dive into those again in the QA if anyone has any questions about it. Now, obviously, I mean, we're video people, right? Like, I'm sure some of you guys heard this, said, okay, yeah, that's kind of cool, but that's old. That's, Sodexis was doing that for years. And you're totally right. And there are best practices for doing it and reasons why we actually always want to do test object based CDN performance measurement. One reason is because the object size is normalized, so we really truly are comparing apples to apples. Whereas with video streams, there's lots of fluctuations, and it gives us the ability to measure a given user on a given platform in a given network and geo as mapped to multiple CDNs. So at the same point in time, we can see how they would have performed had they been mapped to CDN vendor A, B, C, or D, even if they were on E. But that said, it's totally valid point that gets raised often that, okay, well, this isn't real stream data, right? This is all test objects. It's representative of video streams. It correlates with buffering, but it isn't buffering. It isn't start time. So we said, okay, what is the best way to get the video player performance data into our decisioning pipeline? We had a few options, right? We could scrape the QoE vendor SDKs. We can get some custom events from the video player, or in the spirit of, what I had originally sort of started the presentation with, around combining our different sort of siloed products, we can leverage and recycle the real-time CDN log data that we were already collecting for operational visibility and bring it into our decisioning pipeline. And that's exactly what we're doing. So we've just started taking CMCD data and generating a few metrics from that data. I'm going to dive into exactly what those are to extend our decisioning pipeline to include true client performance data. It helps greatly with data blind spots. And what I mean by that is there's a lot more CDN log data than there are test object beacons or performance beacons from the Doppler client, just given the volume of video stream requests. But also there are platforms that we do not have Doppler running on. We can't run that JavaScript in a lot of native apps. And we've thought about extending it to, run in iOS and Android environments, native app environments, Roku, these sorts of things. But it really doesn't make sense to go that route if we're already collecting the CMCD data. So in areas where we're missing, in geos and ASNs where we're missing test, performance beacon data, we're now supplemented with CMCD data, which I assumed a lot of the audience here will be familiar with the CMCD parameters and the various fields, but essentially we can get things like buffer length at any point in time, buffer start, whether or not the buffer or whether or not a session had experienced a rebuffer between object requests, the encoded bit rate, the measured throughput from the client. These are all valuable pieces of data that we can kind of aggregate at that same GeoASN level and combine to provide better heuristics for decisioning and a different view into performance. And then ideally down the line, once we really tune this, we will still do test object downloads, but we'll really dial that down to an absolute minimum. So you've already seen us kind of reduce the number of requests by 75%, there's probably room for us to reduce it by another 50 to 75% from where it is once we really tune, this pipeline. But specifically here, we're looking at throughput today. So there's a field in CMCD called measured throughput, and we are combining that with our Doppler defined calculated throughput, which is in one of those linked docs that I sent. But we know we can do better than that, and we want to do better than that, right? Throughput is good. It's a solid data point for basically measuring the health of the line, right? The line delivering the video objects, but the video player itself might behave differently, and may, the ABR will be different. So we want to really take advantage of the fact we're closer to the player, and not only collect TTLB, but generate a buffer health metric. There's an RFC that we've shared with folks in the industry. So Yuri from Bright Cove, Will Law from Akamai, some others from Amazon, have all kind of contributed to this. But basically what we're trying to do is say, okay, CMCD, cool, lots of great data at the request level. But how can we combine this data and make useful aggregate metrics, or even if you're looking at it only at the session level, just metrics out of this data that's a little bit more meaningful than looking at a timeline of requests. So we came up with a few. Buffer drain rate was the one that I was kind of most excited about in the beginning, only to learn it was actually probably one of the most least effective. But essentially what we were trying to do with buffer drain rate was calculate the rate at which buffers are growing and shrinking in terms of seconds of video in the buffer over time. Once again, for decisioning, it would be at that GeoASN level per CDN. We also came up with a buffer health. We call it buffer health score, but it's a ratio of throughput to encoded bitrate. We looked at buffer length decreases over time. So regardless as to the rate at which buffers are draining, was there a decrease between 1 minute ago and now? And the last one here, I'll dive a little into it, is the max buffer length decreases, which is actually probably one of the most interesting. But the findings that we have are here below, and essentially what we're showing in the two columns to the right, and I'm hoping it's big enough for you guys to see, is the correlation between each one of these metrics and then sessions that actually experienced a rebuffer or a bitrate downshift. If you read the doc that's linked, I basically said the goal of this buffer health score is not only to route traffic, but also to act as a leading indicator for rebuffering or a leading indicator for ABR fluctuations, bitrate downshift specifically. And what we found were essentially of all of the sessions that we analyzed that did experience a rebuffer, and of all of the sessions that did experience a bitrate downshift, that's what you see in the third or the fourth and fifth column here. We were able to capture those with the given metric in column A. And so basically what we found was, of all of the sessions that we surfaced by looking at buffer drain rate, less than 1% of them actually had a rebuffer. Of all of the sessions that we analyzed according to buffer drain rate, 44% of them, pretty good, did have a bitrate downshift. 44% of them associated with a buffer drain had a bitrate downshift. That's good. It makes sense. I would have expected to see the rebuffer number be higher, but we did the same with each one of these different Oh, we have to wrap up soon. Okay, yeah, thanks for the time check. Taking the max buffer length, decrease over a period of time, or 30 seconds, actually was the best indicator of buffering, both buffering and bitrate downshifts. I'm gonna skip through these quickly. I could dive into that if anyone's interested, but all that's defined in the attached doc. Issues with DNS is a big thing that we see fairly often. I'll go through this very quickly, but essentially, Cloudflare breaks DNS-based decisioning and leads to a lot of CDN flapping, which is a problem we experienced during Super Bowl, and it's a problem we experience day to day during live events. Oblivious DNS, ODOH, VPNs, they exacerbate the issue. The problem here really is that DNS providers don't support eDNS, and even for those that don't support eDNS, some of them are fine, but a lot of them don't act as good proxies for a client's geo. So in the case of Cloudflare, essentially what we saw was every time a DNS lookup happened, sometimes our authoritative DNS server would see the client as coming from the East Coast, sometimes West Coast, and because of the way we do all of that CDN stack ranking and routing, we would flap between CDNs because everything was aggregated at the geo level. It's exacerbated, like I said, by VPNs and next gen DNS, technologies. So really, our goal is don't rely on DNS. Integrate with either a manifest generation service or content steering. Content steering, there's an awesome demo that Yuri from Brightcove put together here, where essentially he's actually putting the content steering server on two different edges, which is pretty cool. This is what we're planning on implementing and slowly sunsetting DNS-based decision, because it simply doesn't work. And the more people care about privacy, which in my opinion is the future of the internet, the more problematic DNS-based routing is going to be for video workflows. We do have an integration with our manifest generation service, but the big thing here is, works great for live, which is what we're talking about, but it doesn't work for VOD because we have to do all of that decisioning up front, right? And it would be based on the performance at a point in time when the master manifest or the initial request is sent out. With live and the manifest getting updated every 6 seconds or segment length period of time, it works just fine. I had a whole other section here on piracy and how we've kind of combined these products to surface vectors of piracy, and then offer a session revocation endpoint. I did get a time check note, so I just want to, I guess, check in. Am I good to continue, or should we call it?
We have to close it down pretty soon, just because the venue itself is closing soon. Sean, can you hear me? He's on mute.
Oh yeah, sorry. What was it? Okay. Yeah. Okay, just feel free to. Yep. Feel free to cut me off if anything. Do you mind muting? Because I'm bad at. Oh, okay. Yeah. So I mean, the piracy stuff, I'll just leave it at. We implemented a token, a common token schema similar to the CAT. That's SVTA, CTA, common access token. There's a demo here that shows exactly how it works and how we're able to use that same visor data along with the not just the CDN logs, but the DRM logs to surface vectors of piracy, surface anomalies, and then actually revoke the sessions. So I'd suggest taking a look at this, and happy to talk about it if you guys are interested. Cool. Thanks. I don't know if we're going to do a QA. All
We'll
right.
take one or two
Cool.
questions if there's any in the room. If not, I can catch you up on stuff that he's talking about or connect you with Sean if needed after. Can we get a copy of the presentation, Sean?
Yeah, sure.
Okay, we'll get that put up. Yeah, all the data we can look at. I work with Sean on this stuff. We're starting to work closer on the non-DNS-based client-side decisioning here in the future. So we'll try to get info. Go ahead. How are we dealing with cache low latency content? The cache header is less than. It's a 1 second.
Yeah, so we're not doing any low latency. And that probably would add complexity to this, but essentially our way of dealing with latency has just been to reduce our segment size, and it's worked fine for our needs. Yeah.
All right, thank you. Any other questions? All right, thank you so much, Sean. Big round of applause. Thank you so much for doing this. All right, have a great night. I'll talk to you later, Sean.
See you.